Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Angus Lowe from MIT, who will talk about randomized truncation of quantum states. So Angus is a PhD student at the Center for Theoretical Physics at MIT, advised by Aram Harrow. And his interest is in like quantum algorithms, learning properties of quantum states, and general quantum information theory. Before MIT, he completed a bachelor's in science in computer science and physics at the University of Edinburgh, and a master's in math at the University of Waterloo. And he also previously worked as a quantum algorithms researcher at Xanadu. So Angus, the floor is yours.
Thanks so much. And I think I noticed Hakop in the audience before I stopped being able to see everyone, and we actually overlapped briefly at Waterloo, so just wanted to say hello again because I didn't get a chance to do that before.
Wonderful.
But yeah, thank you so much for the very kind introduction, and I'm very happy to have been invited to speak at this seminar series. Today I wanted to tell you about some recent work on this deceptively simple problem of trying to determine what is the best way to truncate a quantum state. And this is based on joint work with Aram Harrow, who's my advisor at MIT, and also Freek Witteveen, who's based at CWI and QSoft. Yes, before I begin, please feel free to ask questions throughout, especially because I can't see you at the moment. So I'll have to just listen out for any questions. And maybe I'll have a question or two for you at some point as well. So as I was saying, here's the main result. We solved for the optimal randomized truncation to a quantum state. And the main open question left from our work is, what are the applications of this technique that we introduce? And we think that it should be a pretty powerful method with wide-ranging applications to simulating quantum systems, but it remains to be seen how effective it is in practice. And so I think that's the main lingering open question from the work that I'll tell you about shortly. So to set the scene, let me tell you about this basic question that motivates our work, which is, what is the best low-rank approximation to a matrix? And this is a question that you might have seen before because it has many applications to computer science and also quantum information. So here, the goal is to approximate some target matrix M using some other matrix M tilde, subject to the constraint that its rank is at most K. So I guess, yeah, this will be my first question to the audience. Does anyone know the answer to this question off the top of their heads? Here, the norm is the Frobenius norm, but really any unitarily invariant distance measure is fine. Just like, what is the best low-rank approximation to a given matrix? I'm not sure how interactive these seminar series typically are.
Do you have to get like the top K singular value, something like
Yeah, that's
that?
exactly it.
Okay.
So I've given this talk 3 times now, and 2 out of 3 times I've gotten the right answer. So that's pretty good. Yeah, so you take the top K singular values. So if you haven't seen it before, this is what it looks like, pictorially at least. And here sigma is the diagonal matrix of singular values. And suppose that K is equal to 2, then the optimal strategy to approximate the target matrix M with a rank 2 matrix M tilde is just to keep the top 2 singular values and throw away the final one. And this is called the Eckert-Young theorem. Now, in case you haven't seen this before and you're a bit skeptical, you can also just use the eye test by applying this logic to something that's a little more familiar to you, perhaps, which is an image. So suppose that you have some original image that you care about, and your goal is to compress it by keeping a subset of the singular values, which correspond to the matrix that describes the image. Then one strategy is like maybe you keep the top 10 singular values, and then that gives you the approximation that you see on the right here. And as you can see, it's sort of a faithful reproduction of the original image, although compressed, obviously. So that's one technique to compress an image. And as you can see, if you keep like a random set of 10 singular values, that does a lot worse. This is a very visual way to see that. However, and this alludes to what comes later in the talk, this does not necessarily entail that you're dead in the water here. So yeah, let me recap. So I wanted to illustrate the point that the best deterministic approximation to a given matrix, if it's constrained to be low rank, is to keep the top singular values. Hopefully that makes sense. And that's what I've done in this image here. And this is one way that you can compress an image. And to contrast this with a case where you take random singular values, I've done that over here. And the result is less impressive, but I wanted to make the point that you're not dead in the water, even though this image does not take the top 10 singular values. If you choose the distribution over the random singular values carefully, you can form an unbiased estimator for the original. Something went wrong, try sharing again. Okay. Yeah, you can form an unbiased estimator for the original image that you care about, or matrix that you care about. And by taking many samples, you'll converge to the true image. And to contrast the two approaches, in the case of the deterministic truncation to the top 10 singular values, you've got no variance because it's a deterministic truncation, but you've got some bias. And in the case of the randomized approach, there's no bias because it's an unbiased estimator in this case, but it has a large amount of variance. And this already illustrates something that is going to become relevant later in the talk, which is a bias variance trade-off. And you can imagine that if there's a problem where within the problem, what you care about is both the bias and the variance somehow, then it can help to consider randomized approximations. And as it turns out, quantum states and the trace distance furnish such a problem. So did I get this far previously?
Yes, roughly, yes, roughly, yeah.
Okay, great. So now let me tell you about the quantum version of the problem that I just described, which is what is the best low Schmidt rank approximation to an entangled state? And this turns out to be the exact same problem in disguise, because the Schmidt decomposition is just a vectorized version of the singular value decomposition. And in this case, the answer is the same. You just keep the top k Schmidt coefficients. And this gives you an approximation whose overlap with the original state that you cared about is given by this top k norm, which is the same thing as the 2 norm, but you just truncate to the top k singular value. So here I've assumed that the Schmidt coefficients are sorted in non-increasing order. Maybe that clarifies things. And so the answer is to just do this deterministically. And as it turns out, randomness does not help you. Yeah, does anyone see why? I can say a couple words about that. If your metric of success is the fidelity, then it doesn't help to consider a randomized approximation to the target state. All right, I've given you a moment to think about it. It's because in this case, the expression for the fidelity, if you try to approximate the pure state with a density matrix, is just given by a linear function of rho. And so it's going to be maximized by an extreme point. Like taking convex combinations of pure states is not going to help you to maximize that linear function. And so without loss of generality, the optimal answer is to consider the best deterministic approximation, which is given by this truncated version of the original vector. And this is a problem that shows up all the time in tensor network simulations. So namely, as a subroutine and a common subroutine when you're trying to simulate quantum systems with matrix product states is to truncate the bond dimension. So here I've depicted a matrix product state. And typically what happens in these simulations is you'll apply some local operation and then re-express your state as a matrix product state. And then motivated by the fact that the best deterministic truncation is to keep the top k singular values or Schmidt coefficients, you'll truncate back down to the top k Schmidt coefficients. This is bond dimension truncation, and it happens all the time. And this is used when you're trying to simulate 1D systems or classical simulations of quantum circuits and other tensor network-based methods for simulations. And this is all motivated by the fact that the best approximation measured in terms of fidelity is to just deterministically throw away all the singular values past a cutoff. However, this is not true for other metrics, which is the point of this talk. Any questions?
So in some sense, it's kind of like the property of the fidelity function that.
Yes, exactly. It's like, yeah, it's comparing the overlap with a fixed state, which is the target state. And so more generically, actually, randomness in your approximation, in your strategy for approximating the target state is not going to help you if your metric for success is some fixed to linear functional, like the energy or the fidelity. But it will help for worst case error metrics, which I'll describe shortly. In fact, you can see this already when you're trying to, in a different task. So this is not switching away from randomized truncation for a moment. Let me talk about why classical randomness helps if you're trying to approximate a quantum process, which sort of counterintuitively perhaps is like the more familiar example in the literature. Yeah, so classical randomness helps when you're approximating quantum processes. And this is a familiar example from a number of areas. So for example, last year, there was this result by Gauset, Kothari, and Zhang, which stated that if your goal is to approximate the n-qubit Toffoli gate using as few t-gates as possible, then you can do exponentially better if you're allowed randomness, where the metric for success in this case is the diamond distance. Similarly, like a similar fact holds for error mitigation and also in Hamiltonian simulation, where this is sometimes referred to as randomized compilation. So in this Q-drift algorithm, you randomly choose Trotter steps. And let me tell you the resource that you're trying to conserve in each case. In the first, it's t-gates. Maybe for error mitigation, it's noise-free operations. For Q-drift, it's Trotter steps. And in our context for truncation, you're trying to, yeah, the resource of interest is either coherence or entanglement. Yeah, hopefully that makes sense. And you're trying to use randomness to conserve this resource. And now a natural question at this point is why does randomness help for approximating a coherent quantum process? Maybe at first glance, that's a little unnatural, but I can give you two pieces of intuition for this. The first is this geometric picture where you have some fixed target state of interest, or sorry, some fixed target unitary of interest U, and you're allowed to approximate it with some other extreme points on this convex set, which are other unitaries. But you can do better if you're allowed to take a convex mixture of the unitaries. In other words, to go into the convex hull. And this just schematically shows why that's true from like a geometric perspective. And if you're not too convinced by this, the second reason, the next reason is actually a little more helpful from the perspective of proofs. And that's reasoning that comes from two-player games. So suppose your metric for success when you're trying to approximate this unitary process is the diamond distance. That's a worst case error. So you maximize over all measurements and all input states. And if your goal is to minimize this worst case error, that turns into a minimax, which is a zero-sum game. And it's sort of a well-known fact from zero-sum games that the optimal strategy is often mixed. And so the canonical example for this is like a soccer penalty shootout, which is perhaps appropriate given the World Cup coming up. Imagine that you're taking a penalty shootout, and you're right-footed. Then the best deterministic strategy is to just kick left every single time if you're right-footed. But that's not what you should do as the penalty taker, because then the goalie has a hard counter strategy, which is to dive like stage right every single time. And so it helps to mix in some kicks to the right, even if you're right-footed. And maybe that, if you haven't seen zero-sum games before, maybe that gives you some intuition for why mixed strategies are in general the optima, or the equilibrium points. And the same thing is true quantumly. In this case, maybe the goalie is like the player who's doing the measurement, and the kicker is the player who's trying to minimize the distinguishability by choosing a channel in this case. It's an analogy, but it's a pretty close one. Does this make sense? Okay. So now this leads to sort of natural question, which is whether randomness helps for truncation, which motivates the current work. And if you're just interested in whether it does in any case, then this is already sort of clear to see from a 1-qubit example. So suppose your goal is to truncate the uniform superposition to a 1-sparse state. 1-sparse meaning it has like one entry in the computational basis, right? So then I'm going to denote by capital T the trace distance throughout this talk. We get a trace distance. You use either like of the computational basis states, you're going to get 1 over root 2. But maybe you can already see from this block sphere on the right that you're going to do better with a maximally mixed state. If you instead consider the maximally mixed state as an approximation to the uniform superposition, then that gives you a quadratically better trace distance in this case. 1 over root 2 is reduced to a half. And visually, this is already clear. So in this case, the trace distance goes down by a quadratic factor. So the answer is yes, at least in some cases. And by the Fuchs-Van de Graaff inequalities, which are standard inequalities in QI, this turns out to be the best that you could possibly hope to do by mixing pure states. So you're trying to approximate this pure state by a mixture of sparse pure states. I don't want to dwell on this slide too often, but this is just to say that this quadratic advantage that I just illustrated is actually quite generic. It's not particular to this single qubit example. It's just a generic fact that quadratic advantages occur very frequently. There are like pathological examples that you can construct where they don't occur, but this is like one particular experiment you could conduct. If you parameterize the target state as a power law, then in large dimensions, you're just going to find that a quadratic advantage, which corresponds to alpha equals 1, just always occurs essentially, except for like some constant size region. The specifics of this illustration are not too important. You can find more details in the paper, but this is just to give you some sense that the previous fact that I told you about there being a quadratic advantage if you incorporate randomness into your approximation applies more broadly than just that specific example. And in fact, if you choose a Haar random state, this is also true in large dimensions. I'm not going to illustrate that in the talk. So let me recap what I've told you so far, because I've said a lot of things. The first is that truncating quantum states is fundamental and important, and has practical applications. And the second thing is that randomization often helps quadratically, not just for quantum states, but also for quantum processes, which is well known, whether that's for Q-drift and Hamiltonian simulation, or if you're trying to reduce the number of T-gates to implement a Toffoli, a multi-qubit Toffoli, multi-control Toffoli.
Okay, I guess I should have asked this earlier.
Yeah.
So when you make an approximation to a k-sparse state, so
Yeah.
the sparsity is basis dependent?
Yes, although that's a good question. So this is true. But if you switch to talking about the Schmidt rank, that's not basis dependent anymore. And it turns out, because of this Eckert-Young theorem that I mentioned earlier, that without loss of generality, the optimal basis is to stick with the Schmidt vectors. And so you can just consider those to be the computational basis. And so another way of saying this in like resource theoretic language is like coherence and entanglement are sort of the same thing in this truncation, in the context of this truncation problem.
Is this for unitarily invariant measures? Or
yeah, it might be specific. I haven't thought about that, whether it's specific to unitarily invariant measures. We proved it specifically for the trace distance in our paper, that without loss of generality, you can do this. It's obvious for fidelity from Eckert-Young because that's just a vectorized version of the Eckert-Young statement for unitarily. Like the Eckert-Young says for all unitarily invariant matrix measures, matrix norms, the best approximation is to keep the approximation in terms of the singular vectors, like in that basis, and then truncate the singular values. And if you just vectorize that statement, you basically get that the best approximation is to keep the top k Schmidt coefficients. And it doesn't help to consider a basis transformation. And then we showed us like the same statement holds for trace distance. I'm not sure if you can take our proof and apply it to unitarily invariant norms in general. Good question, though. Okay. So this is the setup for the remainder of the talk. How much time do I have left, by the way?
I think like 15 minutes. Something.
Great. Okay.
Yeah.
I'll go through it quickly. I guess the setup is more important than the answer anyway. So here's the algorithm. Sorry, it's not the algorithm. This is what we want from an algorithm. Suppose that you're given a target state, which is d-dimensional, and you have some sparsity constraint, which you should think of as interchangeable by this discussion that we just had with a constraint on the Schmidt rank. And you're interested in some norm, let's consider the trace distance for now. Then what you'd like is the algorithm to output an ensemble of pure states such that two criteria hold. The first is that each of the pure states is Schmidt rank at most k. And the second is this ensemble minimizes the trace distance to the target pure state. Yeah. And the question is whether we can design such an algorithm and whether we can solve this problem efficiently. But a word of caution before I give you the answer, if you change the statement of this problem, it's kind of delicate. If you change the statement of this problem so that the target approximation is also mixed, and then you're looking for the best approximation in terms of a mixture of states, which is at most Schmidt rank k, then that version of the problem is NP hard. And so you shouldn't strive to solve that. And we prove this in the paper, along with concurrent work. Yeah, by a reduction from finding k-cliques. So it's too much to ask for a generic algorithm that works for an arbitrary mixed state. And so this brings me to the main result in our work. Sorry, I'm going through this a little quickly, which is that for a given target pure state, we give efficient algorithms to solve for the optimal randomized truncation in trace distance. And so solve for means with these efficient classical algorithms, you can get the optimal value. You can compute an optimal solution in the standard basis. And importantly, you can also efficiently describe a distribution and sample from it to get a resulting density matrix that is the optimal solution. So all three of these things are true. And maybe I'll give you a second to parse this.
Angus,
And,
do you mind Sorry,
Yeah.
sorry to interrupt, but do you mind minimizing the like your view of us? Yeah, that thing, because it's in the way. Thank you.
Yeah. I'll just leave this here for a second because this is the main result in our work. Okay, and in the next few slides, I'm going to tell you how we do this. Here, efficient means in time polynomial in the dimension. So given some classical description of a target pure state, we give efficient classical algorithms to solve for all three of these. And importantly, the third one allows you to use this method as a subroutine whenever you have a situation where you would like to deterministically truncate a target state. You can instead just employ this randomized version by efficiently sampling from this distribution at a cost that is comparable to the cost of performing the singular value decomposition to begin with, which is like cubic time.
I'm just curious, so if you run this for a problem where the optimal is the deterministic one, would it give the same answer?
Yes.
Or
Yes, that's right. But it might not be the uniquely optimal. So sorry. So you're asking because the deterministic approximation might not be the uniquely optimal one, what is the solution that this algorithm outputs in that case? Is that your question?
I guess we can make that the question.
Yeah.
That seems the more interesting version.
Yeah, I don't think it's guaranteed to give you the deterministic if it's not the unique solution. Sorry, spoke too quickly. So let me tell you how to randomly truncate. So first, let me remind you how you do the optimal k-sparse deterministic truncation. So let's talk about the computational basis because of this discussion that we had previously about not needing to worry about changing bases away from the Schmidt vectors because they're, without loss of generality, the optimal basis to consider. If you assume that the Schmidt coefficients are sorted in non-increasing order to begin with, then the optimal strategy deterministically is just keep the top k up to some normalization. If you want to form an unbiased estimator, here's what you can do. You can pick some parameter r, which determines how many coefficients you keep deterministically. And then you can sample from the remaining coefficients. And if you do this, if you do this with some foresight, by picking the marginal probabilities to be proportional to the coefficients, then maybe you can see that the resulting vector is an unbiased estimator of the true target state. And this holds no matter how big this set is. So here, the red indicates that it's like a set valued. So yeah, this S is a set valued random variable. And the red indicates that this is random. And this holds for any R, like any choice of cutoff for the deterministic. So you can partially keep the coefficients and partially randomly sample from the remainder and do this like importance sampling method. So here, without further ado, here is the optimal way to truncate a state. It's to keep some coefficients deterministically, just like in the unbiased estimator, the case of an unbiased estimator, randomly sample some of the coefficients, and then drop the rest, and then adjust the marginal probability so that they make sense. Now, this requires you to solve for some parameter lambda, but you can do that efficiently. And the lambda coincides with the optimal value for the optimization problem. In other words, it's the minimum trace distance over all k-sparse mixtures. And L and R are some parameters that also come out of the optimization. This optimization is just iterating over KKT points, essentially, for those who are familiar with the convex optimization terminology. And so this is it. This is the family of states that you need to consider if what you care about is minimizing the trace distance. It's a bit weird. It's like a three-part thing where you deterministically keep some coefficients, you sample some in the middle, and then you drop the rest. And you have to solve for these cutoff points. I can't see if there are any questions, but please let me know if there are.
Maybe I'll ask a question,
Yeah.
Angus, if you got that. So is there any overlap between the ones you're sampling and the ones you've deterministically kept? Or are they disjoint? Are these three sets disjoint?
Oh yeah, sorry. These are three disjoint sets.
Okay.
You're partitioning the set of all coefficients that you could have kept.
Right.
Yeah. And solving
And
for these cutoff points.
I see. So can you explain how that solving works? So I assume like the ones you throw away, like there's maybe exponentially many of them or something, right? Like, well, sorry, you're working in like like some fraction of D is maybe thrown away. Is that right?
Yes. So
Can you?
all our efficiency statements are in terms of D. Like D is the size of the input
Yeah,
here.
that's why I kind of had to readjust. Yeah, I normally think of D as exponential, but yes.
Yeah.
Can you just say something about how the cutoffs are determined again? I think you said something very briefly.
Yeah, so I'll describe it in words. It comes later, but I'm not sure I'm going to have time to get to it. So let me describe it in words. You iterate over all possible choices of R and L. There are only D squared of them, right?
Mhm.
All possible R, all possible L. Well, there's at most K choices of R. So, and K is less than D. Similarly for L. It's in any case at most D squared. And then you do this iteration through all possible choices. And these correspond to possible KKT points in an optimization. And there's like a necessary condition for the optima to satisfy. It's like a first order optimality condition. And if any choice of R and L satisfies them, you're guaranteed that that's a valid choice for the optimal solution. That's quite rough, but basically you just guess and check every single R and L, and there's a sufficient condition that you can check. There's a cubic equation that you can solve that allows you to solve for lambda. And if the lambda is non-negative, then you know you've hit the right one.
Okay.
This is
okay, maybe I
this is
can ask,
very
is there any intuition you can kind of give us about what's going on here? Like I assume when you throw stuff away, you're kind of creating a bias. When you lock stuff in,
right.
when you throw stuff away, you're creating a bias, but you're reducing your variance.
Right. So in the unbiased case, there was zero bias, but some variance. Clearly, there's like some bias and variance going on here. And that's because the trace distance cares about both the bias and the variance of the estimator for the state that you get corresponding to the density matrix. In terms of like intuition for why the trace distance cares about both bias and variance, I think that goes back to the zero-sum games, but I'm not sure I could do a convincing job in the time that I have remaining while just remaining on this slide, to be honest.
I can kind of see
conveying some intuition.
Thank you.
But the distribution over possible indices J1 through to JR plus 1 could be an exponentially long vector in D. Because there is almost like you run the risk of there being D choose K such subsets, and you need a probability of choosing each one. And so a priori, it's sort of unintuitive that you can even with this solution in hand, that you can efficiently sample from the right distribution. And so that was what the rest of this talk was supposed to be about. Let me briefly flash the solution, assuming I have like 5 more minutes. Is that okay?
Yeah, sure.
So it turns out that the optimal solution over the indices to choose from is the Gibbs distribution. So let me remind you the problem that we're solving here. I've told you that the optimal solution to this problem of randomly truncating a quantum state is to deterministically keep some, deterministically drop some, and sample from the remainder. But sampling from that remainder can, in general, involve keeping track of a probability distribution, which has a length that is exponential. It's like d choose k in the worst case, or d choose r plus 1. So let me switch notation a little bit. You can represent such distributions as like sampling from fixed Hamming weight bit strings. And it turns out that the family of probability distributions that gives you the optimal solution for the truncation problem is the Gibbs distribution. This comes from a maximum entropy type argument. So for the physicists in the audience, this is kind of like if you get the Gibbs distribution from maximizing the entropy subject to an average energy constraint. Here you're like fixing the occupation numbers for non-interacting fermions. And then you want to find the Hamiltonian that, you want to find the corresponding Hamiltonian, which is equivalent to maximizing the entropy. And so we provide improved algorithms to solve this problem. And this is the problem that you need to solve as a subroutine to efficiently sample from the distribution to randomly truncate. So I do want to tell you more about random truncation. I feel like it was a very high level picture. So please feel free to ask any questions that you're curious about. I can flash.
Just a quick question. So just to clarify, sorry, I couldn't quite understand the details of how this Gibbs distribution is constructed. Can you just say it's obviously correlated? It's not like a product distribution.
No, yeah, it's not a product distribution.
Sorry, it's not.
It's not a product distribution because you have the constraint that they're fixed Hamming weight bit strings.
Right.
So it's not. But this is equivalent to, this is called conditional Poisson sampling in the survey sampling literature. That's a terrible name because they're not Poisson random variables. They're Bernoulli random variables. I don't need the slides. I'll just tell you. Or actually, maybe they're helpful. They're Bernoulli random variables. So it should really be called conditional Bernoulli sampling. And the task that I just described to you is equivalent to sampling from independent Bernoulli random variables subject to the constraint that there's a fixed Hamming weight and you know the marginal probabilities. So that's some correlated distribution. But you can efficiently solve for the Bernoulli parameters or equivalently the energies in this Gibbs distribution. And we give a faster way to do that, which is like a purely classical problem, but it's very relevant for the randomized truncation subroutine. Because the ultimate goal is we'd like to get these subroutines to have runtime that's on the same order of magnitude as the singular value decomposition. Because that takes cubic time. And if you can argue that with an overhead that's like negligible compared to the cost of doing the SVD in the first place, you can do the optimal randomized truncation. That would be very nice. And so that was our motivation for like improving these purely classical problems about like the runtime for classic sampling problems, or very natural sampling problems. Yeah, it's been an hour already, I guess, since I rejoined this talk. So maybe we're over time.
Thank you very much, Angus. I've actually got to run to another meeting, but thank you very much for the talk. That's great.
I just wanted to ask like one question maybe before we go. I'm just curious, so when you have these 3 disjoint sets, right? So there's a deterministic part, a part where you sample and what you cut off. So is that a property of the psi, like the target kind of state, like the state that you want to truncate? So it feels like when its coefficients in the Schmidt basis has some like certain distribution itself, then you can already predict like what is the R and L that you would need, or is it like there's always many choices of R and L, but then it changes the distribution that you would need to use for the sampling?
There's only one choice of R and L, as it turns out.
For every kind of like state you want.
So long as, yeah, yeah, there might be, if there are degenerate coefficients, then it's possible that R and L, there might not be a unique R and L that solves the problem.
Okay. But
Yeah.
beyond that, like once you find like what is the correct R and L, as you say, like you still need to know how to like get the distribution, right? Like to sample the things correctly.
That's right. Yeah. So like the train of logic is as follows. You first solve for the optimal RL and the optimal value, the trace distance. Then that gives you like the marginal probabilities in this max entropy problem. Then you have to use the marginal probabilities as an input to get the right energies in this Gibbs distribution. And then that tells you how to sample from the randomness that's required for the random truncation. So hopefully that made sense.